Okay, so this mini lecture is going to introduce the idea of electric flux. Now, electric flux is simply described as the amount of the electric field that passes through a surface area. So the amount of the field, the amount of the electric field that passes through a given area. All right. Now, you might think, okay, wait a second. How that electric field is oriented relative to how the area is oriented might influence the amount of electric field that passes through. And you'd be right. So the electric flux isn't just about how much electric field is around and how much area is that it's passing through in that space. The orientation of the field relative to the area makes a difference. More specifically, if you imagine an electric field, and I'm just going to draw a parallel electric field here designated by our pink line. So here's our electric field. And let's use a rectangle, keep it simple. And I put a rectangle parallel to that electric field so that the electric field lines are running parallel to that rectangle. You can imagine an amount of electric field that passes through that might look different. Let me extend these electric field lines a little bit. Than if that rectangle was orientated at an angle. And I'm gonna try to draw this maybe there. I don't know, does that look like it's at a steeper angle? Sure. All right. And of course I drew it too high. So let me add a few electric field lines in there. All right. So imagine that in this case, the rectangle is perpendicular to the field. And in this case, the rectangle is angled at 30 degrees with respect to the field. Which one is going to have kind of more field lines going through it? You might imagine that it's the one that's perpendicular. When I'm perpendicular to that electric field, you can imagine all those field lines are going through it. If I turn my area at an angle relative to that electric field, then it's almost as if it's not as effective for those electric field lines to go through, and it's really a projection of that area on the electric field that is perpendicular to those field lines going through. And that's how we deduce what the relationship is between electric flux, the electric field, and the area. The electric flux, which we designated as this phi, is equal to the electric field in the dot product relationship with the area. So it is the perpendicular component of the area, or said another way, the perpendicular component of the electric field to the area that gives rise to the electric flux. So I'm going to use my angle of 30 degrees. So if this is let me use a different color, I'll use blue. If this is the direction of the electric field, which of course it is, then the perpendicular direction relative to the area is what gives rise to the electric flux. So this can be rewritten as the electric field strength times the area times the cosine of the angle theta, where the angle is the angle between the direction of the electric field and the direction of the area vector, where the angle theta is the angle between the electric field and the area vector. And this area vector is the direction perpendicular to the plane that area is taken. So if this rectangle is at an angle of 30 degrees with respect to the electric field, this angle theta is our 30 degrees. All right, let's use an example to practice using this equation. And then we'll talk about a couple of different ways we can think about what this means, this electric flux idea. So let's imagine going to pop up an example for us. Let's imagine that we have a rectangle. We'll use a rectangle that's 20 centimeters by 30 centimeters. And it is orientated at 30 degrees with respect to the electric field of a magnitude 200 newtons per coulomb. So how can we use our new understanding of electric flux, which is E dot A, or E times the electric field, times the area, times the cosine of the angle between them. So first we always have to make sure we know what that area is. This is the area of a rectangle. It's the length times the width. So we have 0.2 centimeters times 0.3 centimeters. And we calculate our 0.2 centimeters times 0.1 centimeters. I said the wrong thing. Times 0.3 centimeters is our area. 0.1 times 0.3 is 0.03 centimeters. That's our area. Our electric, so we're going to plug that area into here. Our electric field we have is 200 newtons per coulomb. We'll keep the units out of that. 200 times our area of 0.03 times the cosine, as the problem says, of 30 degrees. And we find our electric flux to be 3.5 newtons times meter squared, areas in meter squared, per coulomb. All right, so a couple things to pay attention to. First, our area, if we're going to use newtons per, if our field is in newtons per coulomb, our area needs to be in meters squared to sort of get that standard unit of flux, which is newtons meters squared per coulomb. Okay, pretty straightforward example of how we use electric flux. Now, another way to think about electric flux is in terms of the number of field lines. If we imagine this field, isn't that field lines going through our area, the number of field lines is really the equivalent of our flux. And so the number of field lines is also proportional to the electric field times the area times the cosine of the angle, or proportional, of course, to the electric field dot the area. So we might also think of it in this way. So the electric field, we can imagine, as we learned in the electric field lecture, that those are a whole bunch of field lines of equal potential. Those field lines are proportional. The number of those lines are proportional to how strong that electric field is. More strength, more field lines, imagine that, dot the area. Okay. All right. This is all great if our field is uniform and our surface area is flat, but what if it's not? What if our field is not uniform and our surface area is curved? Well, we can use the idea of calculus to get at what is the electric flux. So let me just get this erased and then reintroduce that idea. And again, this idea is what happens if our field isn't uniform or our surface isn't flat, or both. Okay, so non-uniform field. Let me get rid of the problem. Non-uniform field or a non-flat surface. So let's say imagine I have a curved surface and a non-uniform field. If I take that curved, or this, what if that's the shape of my surface? And I dive down into that surface and I look at a tiny little area. Well that tiny little area, that kind of looks flat. And if that tiny little area, we'll call that delta A, if that's really, really small, then if I have a field that's non-uniform going through here, but I zoom into this tiny area. At this small area, the field actually is uniform, or can be approximated at uniform. So if I look at a tiny little area with a tiny little space, that means the field is going to be more or less uniform in that small space. And then if I just add these up all over the course of that area, then I should get the flux through that whole area. Well, that transforms our relationship of the dot product for a uniform field and a flat surface to an integration with respect to that small a. And so using the ideas of integrating over tiny areas, all the same size, where those tiny areas can be viewed as flat areas with a field line that approximates uniform in that small space, and I integrate over that, I can get the flux even in a non-uniform space. And this is our basis for Gauss's law, which is going to be a different in our subsequent lecture. All right, so flux is simply the idea of an electric field passing through an area. We can look at all different shapes of areas. How that area is orientated relative to the electric field gives rise to how large the flux is. And kind of think about it in terms of the number of field lines. And if we have a non-uniform area, a non-flat surface or a non-uniform electric field, we can use the idea of integrating along that area, small little areas along the entire area to get a sense of to calculate the electric flux through that non-uniform area. All right, good job.